Hello students, in our classes discussion class, we were studying plane diffraction grating and diffraction due to an slit, right? So whoever not watched the last videos on this topic, please go and watch those videos because we will continue our discussion from here on. Okay, so actually let's have a little recap on this. We were discussing about the diffraction due to an slit. So we had two phenomena here. First one is interference of the wavefront passing through these slits, and second one is wavefront passing from these slits, and the second one was diffraction, and diffraction is all the secondary waves particles passing from these slits are interfering again there. So if I talk about the phase difference, then the phase difference for the diffraction, we calculated the phase difference for the diffraction. This was the phase difference for the diffraction, and because of this we will have because of this phase difference, when the secondary wavelet source superimposed further at any point having this path difference, they will tend to have some minima and maxima points. Then with respect to the interference phenomena, the path difference came out this, and the phase difference with respect to this is this. Then we superimposed all these waves and all these secondary wavelets, so all these wavefronts, in which there was one portion of the resultant due to diffraction, and this was the factor arising from interference. So then further, then we calculated that for the maxima points and minima point, we needed to find out the maxima and minima. So for the point to find out the maxima and minima, we just use this factor, and with respect to beta angle, because beta angle determines the maxima and minima points, we actually did a derivative of this, and after putting that derivative equal to 0, we got one substantial condition. This was our condition. This one was our condition. So here we have two things. First thing is this, and second thing is this is our first thing, this is our second thing. So using these two equations, for the principal maxima we calculated principal maxima. When we put the denominator sin beta is equal to 0, we get the principal maxima, and the principal maxima we calculated that the intensity of the principal maxima is directly proportional to n square, the number of lines exposed to the wavefront, initial wavefront. Then we calculated the position of principal maxima, and we got this equation that a plus b sin theta n must be equal to n lambda. With respect to n and 2, we calculated what should be the angular theta value. Okay, then we calculated for minima, and for minima of this equation we put from this equation we put sin n beta is equal to 0, with the condition that beta should not be equal to n pi, because corresponding to beta n pi we have principal maxima. So n beta, from here on, sin n beta is equal to 0, that implies n beta should be equal to m pi, and m has these integers values. M cannot have these integers values 0, n2, n, because at these values we have principal maxima. So if we in between from 0 to n, look, if our n is 10, then between 0 to 10 we have how many integers? 1, 2, 3, 4, 5, 6 and 7, 8, 9, 10. So we have n minus 1 minima points in between 0 to n. Then n is not allowed, then n to 2n, again we have those n minus 1 points. And with respect to these n minus 1 minima points, so equally spaced, and these are equally spaced minima with between two consecutive principal maxima. So here is our maxima, here is our maxima, and again here is our second maxima, second principal maxima. Remember this is principal maxima. We will also get some second maxima as well. So if the intensity of this is something like this, intensity of this is something like this, then there are some minima and maxima over there, and the minima, these minima are from 1 to this minima, we have n minus 1 minima here. Similarly, we will have n minus 2 maxima here. Now these maximas are not equal to this. These maxima intensity is not equal to this, the secondary maximum intensity. Okay, so if we try to find out the secondary maxima positions, then we will use second equation of the second portion of this equation, n cot n beta minus cot beta is equal to 0. Using this equation, n cot n beta minus cot beta is equal to 0. So all the roots which does not account beta is equal to n plus minus n pi, which correspond to the principal maxima, they give rise as the secondary maxima. So all the angular values, angle beta angle value which leaving plus minus n pi, we will have secondary maxima. Okay, and those should be the root of this equation. We need to calculate this equation. So further calculating this equation, to find the intensity, we will evaluate this fraction. So we got this condition that implies from here on n cot n beta is equal to cot beta, that implies cot n beta is equal to cot beta by n. So if n beta is the angle, and according to trigonometry and geometry, if this is the angle n beta, then cot, and this is cot beta, our base is cot n beta is base by perpendicular. So if this is cot n by n is equal to cot n beta, this angle, that implies this hypotenuse is equal to n square plus cot square beta, root of this. Then sin n beta comes out to be now we got cot n beta is equal to this much. So this angle has some values with respect to these. So from this triangle we can find out what is our sin n beta. So for sin n beta, we must have perpendicular by hypotenuse, right? Perpendicular, which is n upon hypotenuse. And what is our hypotenuse? This is our hypotenuse, root of n square plus cot square beta. So sin n beta comes out to be like this, and we need to evaluate this factor, this particular factor. What is the value of this? So sin square n beta dividing by sin square beta in both of the sides, sin square n beta by sin square beta is equal to n square upon this, which is n square upon this, by just putting the value of cot square beta and multiplying this factor inside, we get n square by n square sin square beta plus cos square beta, and this comes out to be n square, putting the cos square beta value as 1 minus sin square beta, and by calculating this we got n square 1 plus n square minus 1 into sin square beta. So now this is the intensity. Now if I put this value in this relation, we got one relation that I is equal to a naught square sin square alpha upon alpha square, then sin square n beta upon sin square beta. Now this was the intensity at any point putting the values of beta angle, right? So with respect to different beta, we get minima and maxima. So correspondingly we got the condition of principal maxima and minima points. So now if I put this value for secondary maxima, if I put the value of this equal to this into this equation, I will get intensity of the secondary maxima, obviously. Now this secondary maxima intensity is not quite similar to the intensity of principal maxima, because intensity of principal maxima came out to be a naught square sine square alpha upon alpha square into n square. So the ratio of these intensity comes out to be something like this, and intensity of secondary maxima to the intensity of principal maxima. Okay, so that's why we can say from here we can compute that intensity of principal maxima is not equal to the intensity of secondary maxima. Secondary maxima points have lower intensity than the principal maxima's intensity. Okay, so further in this relation, if we increase number of slits, and then in intensity of secondary maxima related to the principal maxima decreases and becomes very poor. For large value of n, like in our experiment we used 15,000 lines per inch or 500 lines per mm. So the n value comes out to be, now this is our n value. For large n value, we will observe that the secondary maxima, we cannot distinguish secondary maximas, and for smaller n we can observe those secondary maxima quite. Now for the position of secondary maxima, we again use this kind of equation. By solving this equation, converting it to tangent form, we will get n tangent beta is equal to tangent n beta, and by considering that both the values are equal to y, then plotting y with respect to n tangent beta and tangent n beta here on. Now this is the graphical representation of n tangent beta, and this is the graphical representation of tangent n beta. Okay, so from here, wherever these cuts, we will get this particular position, wherever these thing cut, these lines cut, we will get the position of secondary maximas. Similarly, at those locations or at those values, beta values, we can find out the secondary maxima intensity. So plotting here all these values, now these are the principal maxima, these are our minima points. Okay, these are our minima points, and these are our secondary maxima points. The intensity of the secondary maxima is very small than this. Okay, so this is the complete explanation of Fraunhofer diffraction due to n slit, due to a plane diffraction grating. Now there are some other things in this topic as well. Some absence spectra in the grating, absence spectra in which if the minima of the diffraction minima falls on the interference maxima, then we will not see that. So for the diffraction maxima, a plus b is the sine theta n is equal to n lambda is the condition. For diffraction minima, this is the condition, and putting this equal, we get this is equal to, for this theta angle we will get the absence spectra. So this is a plus b by a, so condition comes out to be something like this, that at these values we will have some absence spectra for these a and b values. Now a is the opening of the slit and b is the distance between the slits. Okay, now from mathematical arrangements we can find out the width of the principal maxima. Now the next important thing is the determination of wavelength of a spectral line using diffraction grating, and this particular setup you did in experimental lab as well. So we understood this already, and you can try and study this one, because in experimental arrangements we studied this one, and we did experiment in which we try to find out the wavelength of sodium light using this plane diffraction grating. Okay, so for different n is equal to 1, n is equal to 2, and n is equal to 3, and so on, we get different angular separation values, and then we just put that in this equation. For n is equal to 1, this was our value, that a plus b sine theta 1 must be equal to lambda, and for the second order. So the arrangement is done by the Schuster method, and we did this experiment on the spectrometer, and we studied this using this diffraction grating, that the wavelength can be found out using a wavelength of any source can be found out using plain diffraction grating. Okay, so the next topic of our discussion will be dispersive power of the grating and dispersive power of telescope. Try to understand this, because this is the most important derivation, and to understand this you need to study diffraction due to single slit, diffraction due to double slit, and then only you will be able to understand diffraction due to n slit. These are the three derivations in your chapter. The another important two derivations are dispersive power of the grating and dispersive power of the telescope. We will try to understand in the later classes. Thanks.